them come back. Okay. Am I audible? Am I audible to you?
Yes, sir. Yes, sir.
Okay.
Okay. Is my screen visible?
Yes. Others, please comment.
Okay. Uh, so we are starting. The first question is the dynamic behavior of the liquid level in each leg of manometer tube responding to a change in pressure is given by. So basically, this is differential equation of second order, which response follows, where h dash t is the level of fluid measured with respect to initial steady state value, p dash t is the pressure change, and r, l, g, rho, and mu are constants. So for change in pressure, we have corresponding change in height of manometer. So what basically we need to do is rearrange this equation into standard gain time constant form and find expression for k, tau, zeta in terms of the physical constant. So we need to derive values of tau, zeta, k, and in terms of mu, rho, r, and other constants. Second, for what values of physical constant does the manometer respond oscillate? So basically we need to find the value of zeta in which the response will oscillate. And the third, would changing the manometer fluid so that rho is larger make so density is larger makes it response more oscillatory or less. Repeat the analysis for increase in mu. In case of third, we have to find if we change the uh, fluid, then what will its effect on the oscillation, specifically for density and for viscosity. So start. Sorry.
So any questions here? Anyone, any questions before you start solving? You wanted to address it right now. The question says you are given an ODE, second order, of course, and so the first part is asking you to arrange them into find the standard second order transfer function and what are the values for the gain, time constant, and zeta. Then, so if you have done that, the next question is asking you to figure out what for the what value the physical constant that the manometer response will oscillate. So oscillation has to do with, you have to understand what does the oscillation would correspond to. So oscillation, in what case you will have oscillation, whether it is over damped, under damped, or critically damped. So based on that understanding, you should be able to figure out the what I would say, what are the values of these variables, because eventually everything would be in physical variables. So then the question asks us, if there is a change in the density, what is going to happen? Make it larger or decrease, or for viscosity. So this is a very straightforward thing. So once you have the zeta as a function of all of this, you should be able to say that. So any questions at the moment from anyone? Any questions? If yes, I think maybe we shall wait for 5 minutes. Is that okay, Sanket and Sarthak? Then we will come back. Huh?
Yes, sir.
Yeah, we can relay the solutions now.
Okay. Uh, So, in order to convert it into standard form, we have to take Laplace of this second order equation, and we know Laplace of derivatives is something is in the form of this s square, h square, and succeeding terms. But since the initial value of other things are zero, so we only retain these terms. And for HDSS, we obtain this on comparing with uh, standard things, C by B, that is K. C by B will give us 1 by 2 rho g. Tau is obtained in similar manner, tau square s square. So 1 by B will give us tau, and on comparing 2 tau zeta s will give us zeta, which is equal to A by B. And when response will oscillate, it will respond, response will oscillate only for the underdamped system. So for this value of zeta, the response will oscillate. And from about third, that what is effect of density and uh, viscosity. So from this we can see that as on increasing density, zeta will be smaller and the response will be more oscillatory. And for mu, that is which is directly proportional to zeta, so on increasing mu, zeta will be larger and the response will be less oscillatory. Is anyone have doubt?
Any questions? So here again, this the fundamentally what you have to do is you have to convert them into the Laplace, huh? Then it would be like k by tau square plus 2 zeta tau s plus 1, huh? Then you will know what is corresponding to 2, what is corresponding to zeta by normalizing everything. So the structure should be k by tau square zeta square plus 2 zeta tau by s. So what is comes in the numerator would be k, and the coefficient of s square would be tau square, and coefficient of s should be 2 zeta tau. So just go up. Okay.
So second,
Go down a little bit. Yeah, go down.
I'm not able to go down.
Yeah.
Okay.
Slowly, slowly. Yes, stop it there. So then you will be able to isolate and figure out the zeta, tau, and things like that. And only k, zeta, tau are the three parameters you need to compute. Okay, so now the question is, what would be the physical value of these numbers when things are oscillatory? So which essentially means that oscillation for a second order system will happen only if they are doing an underdamped response, which means that the zeta value should lie between 0 to 1. So you can plug in the zeta value between 0 to 1 and figure out what is the condition. Okay. Similarly, now you see that there are 2-3 external parameters. Of course, R, L, and all predefined, which is the system parameters, length, radius, and even acceleration due to gravity, which is G. Two external parameters which are directly relating fluid are mu and rho, which is viscosity and density. Okay, so mu and rho, which is viscosity and density. Now the question asks us how they are how the response would be varying with respect to the function of f rho and mu. So you can say rho is inversely proportional, okay, and mu is directly proportional. You like these values in this between 0 to 1. So you can give your answers approximately accordingly what would be the range that you would like to fill in. Is this clear or any issues? Only we have only actually 3 people: Aranya, Bhavya, and Deepak. So, and Ujjwal, sorry. So, please consider this as a very personalized, what do you call, poll. So, if you have any issues, Aranya, Bhavya, Deepak, and Ujjwal, anyone?
We know that the initial values are 0. It is just we assume for easy
Okay,
solution, or
that's a good question. So, at the moment, so go up. So, if nothing is given, you are free to assume that they are 0. Correct? Nothing is given.
okay.
Sometimes some condition would be given, then you may take it. Nothing is given, there is no harm in assuming them to be 0. Good question. Any other point? Because you don't have any way to do it, no? So you may assume that you can safely assume them to be 0 if nothing is given. Sometimes in the question you would say H naught is something else. So then you will have to plug in that number appropriately.
Okay, sir. Thank you, sir.
Is this clarified, everyone?
Yes, sir. It is.
Okay, then thanks. Sanket, you may go to Q2.
Okay, sir. Uh, So for the equation given, this equation, find the transfer function and put it in standard gain time constant form. Assume initial conditions to be 0. As we have done in the previous one, similarly we have to convert it in standard form. That is k by taking Laplace transform by converting into k by tau square s square plus 2 tau zeta s plus 1. For B part, specify values of K where response will convert. So for specific values, the response instead of diverging, it will converge. So we need to find that and discuss the quantitative form of the response of this system, provided unit step input is given over the range 0 to 10 in between 0 to 10. Write the form of the response without evaluating any coefficient. So basically we need not to evaluate constant C1, C2 and anything else.
Okay, so thanks, Sanket. So any questions? Again, the question is all about you are given with a differential equation. You need to convert things into the standard form. Okay, so the question, so that is fine. So the question is talk about uh, what is the value in which the system would converge? The value of k in the system would converge, and qualitative form of response. Qualitative in the sense whether you have over damped system or under damped system or critically damped system by looking at the range. So what do you mean by response would converge? Okay, so you know that you know three conditions of second order system: over damped, under damped, and critically damped. So all this require your zeta value should be either should be greater than 0. So all of them would converge. Your over damped response would converge, under damped response, or even critically damped. All the responses would converge. For that, you require the zeta value should be greater than 0. If it is between 0 to 1, it is under damped. Equal to 1, critically damped. More than 1, it is over damped. So the bare minimum condition for the system to be converged is zeta should be greater than 0. With this, you should be able to identify the value of k. Okay, so now given that fact, okay, can you qualitatively say the response directions? So you can check whether in what condition. So only parameter here is k. With respect to k, how are you going to give these parameters? So that's all about it. I think maybe a few minutes. Okay, so 124, like close to 130. Is that okay, both of you, Sanket? And
Yes, sir.
okay, bye. So let's discuss the solutions. So are you speaking something? You are muted.
Okay. Sorry. Uh, as we have done in previous question, we first need to take Laplace, and since the initial values are 0, we obtain form like this. So as in standard form, we need to convert the must have 1 at this place. Uh, for second part, for which values of zeta solution we converge on comparing with standard, we obtain tau equal to 0.5 and zeta equal to 0.25 k. As sir mentioned, for any positive value of zeta, the solution will converge. So for any positive value of k also, solution will converge. From here we obtain that. And in case of third, for which so for which values of k the we need to find for step change response of the response. So for different values of zeta, from here we find for k zeta equal to 1, or k will be 4, and for zeta greater than k will be greater than 4, and for same in between 0 to 4 for under damped system. So for second order step change, for under damped system, we obtain general solution like this. For undamped, critical damp, we obtain solution this like, and for overdamp, we have solution like this.
So any questions, Aranya, Bhavya, Deepak, and Ujjwal? So the question is pretty simple. You are given with an ODE and you have been asked to find out standard point of convergence, which essentially means that your theta value should be greater than 0. That is the defined value of zeta for second order. We don't know what would happen if theta is less than 0, no definition. So based on that, you can figure out what is the range of zeta and k. And the second part, it just says you have three conditions, and when you isolate your the variables, what you are getting is do k is zeta is equal to 2.25 times k by 4 basically. And if you have given a range of k, then what would be the value of zeta? So it should be over, it needs to be over damped, zeta should be greater than 1. So since it is 0.25 k, k should be at least greater than 4. And for make it critically damped, zeta should be equal to 1, which essentially means that k should be equal to 4, and k should be 0 to 4 to make this under damped. So it's a very straightforward question. Then what are the cases? So zeta less than k essentially means that it's a case when
100.
Go ahead.
So for 0 to 4, it's an under damped system.
Okay. So the responses you can definitely calculate it is second order system. Okay, so you should be able to do an inverse calculation and just use the expressions as given. Okay then, so if is there any question? If there are no more questions, we can go to the next problem.
Okay. Question number third. A step change from 15 to 31 psi in actual pressure results in the measured response from a pressure indicated element shown in figure. This figure. Part A, assuming second order dynamics, calculate all important parameters and write an approximate transfer function in the form. So from this figure, we have to find the values of k, tau and zeta to get this standard form, where R dash T is the instrument output deviation and P dash T is the actual pressure deviation. Part B, write an equivalent differential equation model in terms of actual, not deviation, variables. So again, we need to convert this equation into a differential equation. So our main task will be to find k, tau and zeta from the given figure.
What we are trying to do is you have given a graphical, you have given a transfer function and a graphical response. Now you have been asked to correlate them. So we know, so from the response characteristics we know that it is second order underdamped because it shows oscillation finally converts, and your starting point is given, your peak point is given, the distance between the peak is, everything is given. So, but only the point here is that you will have to now carefully take care what is the deviation variable and the actual variable, whether the steady state value is accounted or what, or something that you have to very carefully take care. But otherwise all the parameters are given, so you can use some of the expressions like overshoot, decay ratio, period. If you have the overshoot, decay ratio and all, you should be able to figure out the values of tau, zeta and k. So then you would get your actual transfer function, and if the actual transfer function is obtained, which means that you would plug in the values of k, tau and zeta. So what they are asking is, please write the what is the corresponding ordinary differential equation. They are not asking you to integrate. So just write the what is the ODE form of the original equation. So I think with this information, you should be able to do it. Maybe we'll wait till 1:45, then we can explain that. 1:44, 1:45, 6-7 minutes. You can try at least. Please try to solve from your side. I hope everybody is there. Oh, all of you are there. Aranya, Bhavya, Deepak, and Ujjwal.
Yes, sir.
Bhavya,
Yes. Yes, sir.
Ujjwal, are you there? Ujjwal doesn't seem to be, but that's fine. Please attempt from your side at least, so that you will come to know the steps. We'll explain you in another 5 minutes, 6-7 minutes. Sanket, please. Go ahead.
Yes. So as mentioned, we need to find the value of gain, tau, and zeta. So from definition of gain, uh, from figure we can find the value of gain, that is 11.2 minus 8, this difference upon the step change we made, that is 31 minus 15. So we will obtain 0.2 mm per psi. Also overshoot. Overshoot is nothing but the ratio of A by B. So uh, ratio A by B. So from figure we can find this value, and from definition of overshoot we will get the value of zeta, and also we can see the time uh, period of oscillation. So it will give, since we have value of tau, we can obtain the value of, sorry, since we have value of zeta, we can obtain the value of tau. Uh, and finally we get the standard form. And for part B, simply we need to take a inverse Laplace of the this value, and need to plug in values. P dash is P plus the value in the beginning, so we obtain solution.
So just a second. So any questions so far? So use this already known definition: gain, change of output by change of input. Overshoot you can calculate by the expression B A by B or B by A whatsoever. And overshoot is related to the damping factor zeta, from which you should be able to get back your zeta value. And period is given. Period is a function of z and tau. Zeta and tau. Zeta is already known to you. Now isolate tau and figure out what is the value of tau. If you get everything, three parameters, tau, zeta, and k, the transfer function is ready. So now you can go to the B part. Okay, so then the B part, what you have to do is the transfer function is given to you. Now you have to go to ODE space. So multiply them, cross multiply. So S square become a double derivative, S becomes single derivative. Again, assuming that all the initial conditions are 0, 0.2 times P. Okay, so now what you have to do is the following. So if you look at the question, I think yeah, go up, prime. Just go up. Yes. So the what they are saying, there's a step change from 15 to 31. And the actual pressure in actual pressure results in the measured response. So the P value, which is what is P prime? P prime is P final minus the steady state value. So the steady state value was 15 and it has been pushed to some 31 whatsoever. So the P prime when you the definition of the P prime should be P minus 15. Now go back, go to the solution. So that would be P minus 15 because that is P prime. So then again you plug in everything and isolate everything, and you will get your R double dot, that's all. So if you don't supply P prime as P minus 15, your expression would be in terms of it would be in terms of the deviation variable, which we technically okay. Also, you check the R. So go to that equation again. Go to the expression. Okay, so now you see the response of R. R's response starts from 8 and finally it converges. So the steady state value of the R is 8. So R prime you define as R minus 8 because that's the starting value. The way, because that was the steady state from where you started your response. Similar to P prime is equal to P minus 15. So you plug in both of them in the original variable, you will get the solution. I think that much only. Any questions here? Aranya, Bhavya, Deepak, and Ujjwal. Any queries? Okay, so if there are no more queries, we can go to the last question maybe.
Yes. So fourth and final question. An electrical heated process is known to exhibit second order dynamics with the following parameter values: K equal to 3 degrees Celsius per kilowatt, tau equal to 3 minutes, zeta equal to 0.7. If the process initially is at steady state at 70 degrees Celsius with heater input of 20 kilowatt and heater input is suddenly changed to 26 kilowatt and held there. That is basically we have made step change. So part A, derive an expression for the measured temperature as a function of time. Part B, what will be the maximum observed temperature and when will it occur? We have given values of k, tau, and zeta. So we need to find its again we need to convert it in standard form and need to plug in these values. And for step change, again as step change is given, we need to convert it into our differential equation again. And for part B, we need to find the maximum temperature. Just in case this is the maximum, so we need to find this maximum temperature.
Okay, so here again the second order dynamics details are given, and what you been asked to figure out the response at some particular time, and also what was that maximum observed temperature. Okay, derive an expression as a function of time. So so some of this expression is directly available. At least you can plug in and stop because you know that it is second order and it is uh, what you call second order, and so you and the damping coefficient also it is given. So from which you should be able to figure out what would be the what you call the dynamics. So so you have been expected to give the expression which is already available for the second order. You have to plug in these variables and figure out, and just write the expression in the complete form. And also the B part you should be able to do. What is the maximum temperature? So that is something you can write. What I would say, considering the second order dynamics. So again, 3-4 minutes, maybe 156 or so. Sanket can help you out. So yes, Sanket, please.
Yes. Uh, as sir said, for step change and for second order, we have standard equation given in book, that is equation number 7.18. Just plug in value of the tau and zeta. So we have equation like this, and since it is in terms of deviation variable, and deviation variable is at any time t minus at steady state, and here steady state value is 70 degrees Celsius. So we obtain temperature equation like this in terms of time. So at any time we can find corresponding temperature. For part B, that is the maximum temperature. Uh, so as in case we can see, if this is the maximum temperature, and it is simply a sum of A plus B. A plus B, uh, and if we common out from A plus B, if we common out B, then we have A by B plus 1, uh, and A by B, wait, and A by B is nothing but the overshoot, and we can calculate, since zeta is given, we can calculate the overshoot, and on plugging in this value we obtain the T max, and B dash is nothing but the ultimate value, and ultimate value we can find from the final value theorem. So T max is a steady state value plus this max value, sum of this we obtain.
So thanks, Sanket. So the first part of the expression is just nothing but plug in something and to get your original equation. Just go there once. No, 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 no. So the solution.
Solution. Okay. Okay.
Yeah. So you only need to plug in the desired values. You have this expression directly available in the textbook or even in the notes. I don't know. Maybe hopefully yes. So you only need to substitute these variables and make this expression correct. Okay, so in the second part, what you is uh, you need to identify the value, which is the max value. Max value would be the overshoot most of the time. So the steady state value plus the original value plus the overshoot value. So this is something that you can do. That would be the total. Acha, so steady state value, the total value, and the overshoot. So steady state value, it is starting from 70. Okay, and A plus B would be the and the value of overshoot. So A by B is the overshoot. So you should be able to calculate the total distance would be A by B times plus 1. So overshoot would become A by B. So you just need to substitute the maximum value. So see, A here is B times overshoot. So B and you got the overshoot. So just plug in all of this variable to get the final value. So it should be easy to get it, and that would be the maximum value of B. So this kind of completes the questions, and if you have any queries, we can of course discuss. Okay, and otherwise we can of course take a we can discuss this in the next class. Otherwise, I think we can close the session for today. If you have any questions, Friday you can refer all of this, and we can use our Friday's tutorial time to have any doubt clearing when you try solving the problems yourself. If there is an issue regarding the theory or anything, okay, we shall be able to resolve those queries on Friday. Any questions? If there are no more questions, I think I shall thank our TS Sanket and Sarthak and the participants. Any questions, Bhavya?